we're talking about how to do Bayesian inference in practice. And after kind of an introduction or review for some of you to just what are the main ideas of Bayesian inference, we looked at, I said there were 4 methods. We went quickly through the exact approach and talked a little bit about this Laplace's approximation, which is saying quick and dirty you can do. Not so useful for science because it doesn't give you uncertainties, except in a kind of a very Gaussian approximation. And then, so really the main workhorses for doing practical Bayesian computation are Markov chain Monte Carlo, which we dug into quite a bit yesterday. And then the other one, which I think is new to a lot of you, is variational inference. So that's what we're going to dig into right now. Okay, so the essence of this variational or VI approach is you first need to define a family of probability densities that are going to balance 2 competing criteria. You want a family that's convenient for calculations and that it's flexible enough to match at least approximately the PDF that you actually care about, which for Bayesian computing is going to be the posterior. So that's not so different from what we do in building a Markov train, right? Because there we pick a proposal function that's easy to sample from. The difference here is we're not just picking a specific function with all the parameters locked in. We're picking a family of functions. So it's a bit more general what we're looking for. But, in terms of the mechanics, it's not so different from starting out to do a Markov chain. So once we've defined this family, then really all variational inference is it's finding the member in that family, so tuning the parameters in that family to find the function that's closest in some sense to the target distribution. So if we just draw a little picture, a cartoon of what we're doing. So you've got some data, and you'd like to find the posterior of the parameters given the data. So this is what we want to learn about and what you're going to do. So let's think of that just as a point. Okay, so what space does that point live in? It's in the space of probability distributions. Okay, so we're going to define a family of other probability distributions that is something that's easy to compute. So I'm drawing it as an extended blob because it's not just one point. It's not one function, but there's knobs that you can turn inside that will move you around this space. So variational inference is really just finding, moving around in this space to find the member of that family that's closest. Okay. So that's if you're within this space, that one there is the best approximation. So this is our approximating family. And this is the target function. Of course, if you can find a space that actually includes the target, then you're going to get an exact solution. Okay? That's not generally going to happen because interesting posteriors are not really going to be covered by nice simple functions. Okay, so variational inference is just like Markov chain Monte Carlo. It's not really anything to do with Bayesian computing. It's just a general technique for finding a member of a family, a function in a family of functions that is closest in some sense to some desired function. Where these are not arbitrary functions. They have to be probability densities. So they have to be things that are whose values are always greater than or equal to 0 and that you can integrate to get a finite value. Okay, so a key part of this is going to be what do we mean by closeness? Okay, we're working in this abstract function space. How do we actually measure the separation or the distance between 2 functions? So we know how to do this in just normal coordinate space, but there's not really a unique prescription for saying how far away 2 points are just in regular Euclidean space. We often use just the Euclidean norm between them, like this, which will work in any number of dimensions. But it would be equally valid just to add up the absolute differences of each component like a metropolis metric, or just to just find the largest single component distance. Okay? I mean, there's lots of different ways that you can define the distance, which are mathematically just all just as good as each other. I mean, kind of the general properties you want is as you get, well, one thing you want is that when you have exactly the same things, if x is equal to y, then you should get 0. And in some sense, as you get closer to the x equals y, then somehow your distance should get smaller. But those are very loose restrictions. Okay, so we need to have a separation in this abstract function space. That's going to be the key to actually to solving this problem. So the separation that we normally use for variational inference is something called the Kullback-Leibler divergence, which is a mouthful, so we always just say KL. Okay, so the KL divergence. And so this is how we measure the closeness of two probability density functions, so Q and P. And remember that the way we'll be using this is that P will be something fixed, and Q is going to be something that's moving around some family here. Okay, and so we have to have something that parameterizes how you move around the family. So we'll need some more parameters. Theta are the parameters that we're interested in. We're interested in learning about, like the age of the galaxy. And these other parameters, the variational parameters, are going to be technical parameters that we use to solve the problem. Okay, they're going to be specific to the family that we choose. Okay, so I've written out the definition for it. It uses this really weird notation, which is a pain to do in LaTeX. So it's Q double slash, or the backslash parallel in LaTeX, P. This is the definition of it. So it's an integral. There's a log of a ratio of probabilities. This looks a little bit like the entropy that Brice talked about yesterday, and I'll come back to that point soon. So I want you to, just to kind of get warmed up here, I want you to discuss in pairs these 4 questions that I've listed here. First of all, is this thing that we've defined as a distance between Q and P, is it symmetric in Q and P? What's the value when P is equal to Q? What happens when either one of these approaches for some value of theta, when either of them approaches 0? And then what bounds can you put on the value of that thing? Okay, so if you're not sitting next to someone, now it's time to stretch, move over, introduce yourself, and then take a couple minutes to discuss. Just jot down some notes of your answers to these questions. You talking politics? You talking politics? You said infinity trumps zero. Okay, so first question, is this KL divergence symmetric? So basically, if I use KL divergence to measure the distance between me and x, is the distance from me to x the same as the difference from x to me? Well, let me just by inspection, looking at the equation here. Okay, x and I are not functions, but is it symmetric? It's not symmetric, but that's kind of weird, right? We want, the thing we're trying to construct is a distance, and now we have a distance that actually depends what direction you travel in. Okay, so that's a little weird, but actually it's not so weird, because whenever you use your phone to get directions, right, it's this different amount of time to go from Santa Cruz to San Jose as San Jose to Santa Cruz, right? I mean, that's not such a weird situation. So it's just a more complicated concept, a richer concept of distance. What's the value when P is equal to Q? It's 0, yeah. Because we get this thing here will always be, that will be 1, and so we get a 0 here. So that's good. At least that makes sense, right? When your 2 points are on top of each other, the distance comes out to be 0. Phew. Okay, so what happens when, let's say, Q goes to 0, but P isn't 0? So we've got a 0 here and a 0 here. So I heard you guys discussing, well, you've got this competition, right? This one is going to drive it to 0. This one's going to drive it to infinity. Which one's going to win? Yeah, right, because this is polynomial and this is logarithmic. So the linear part will win. So it goes to 0. And what about when P goes to 0? It's going to blow up. So that's another manifestation of it being asymmetric, right? In one case, it goes to 0. In the other case, it goes to infinity. So very asymmetric. And we're going to see the consequence of that. It has an important consequence in choosing which. We've basically got 2 distances we've created because the order matters. And so this is going to be important for choosing which one to use for a particular problem. And then finally, what bounds can you place on the value of this thing? Okay, you know that Q and P are probability densities, so that means that they're greater or equal to 0, and they individually have a finite integral. So is there any limit on how big this can get? It's probability density. So P and Q can have integrable singularities. So there's nothing prevents this getting arbitrarily big. Can it ever be negative? Can the integram be negative? Let's start with that. So that can't be negative, but this, yeah. So I mean, if P is bigger than Q, so we're getting the log of something less than 1, so yeah, it can be negative. So nothing prevents the integrand being negative, but if the whole integral can be negative, that would just be weird, because when they're right on top of each other, that's 0, and we don't want to get any closer than that. So it's not at all obvious, but it turns out that this can actually never go negative. So on the next slide, which I'm not going to read through, I put just writing out the solutions there for your reference. What?
I'm just wondering that how do you distinguish the difference when P equals Q and when Q is equals 0?
Oh yeah, so I'm just covering each of those cases individually. So I mean, you're not like combining these now. So yeah, so.
But what we want is P equals Q, right?
Yeah.
Yeah. So if we use this divergency, then when it approaches to 0, which is we want, but how do we know that is the
Right, q equals 0 everywhere.
For all theta values.
Yeah. Yeah, so remember, Q and P have to be valid probability densities. So that means that they have to be greater than or equal to 0. So they can be 0 anywhere. They can even be 0 for, over a whole region. But their integral has to be finite. They have to be normalizable. So you couldn't, that would exclude the 0 everywhere case. Yeah. Okay, so as I said, so on here is a bit more detail about solutions. So for the last one, it turns out that although the integrand can go negative, there will always be more positive part of the integrand than negative. So you never actually get an overall result of the integral that's negative. And that's not at all obvious, and it relies on some useful tricks, this thing called the log sum inequality, and that in turn relies on something called Jensen's inequality, which crops up all the time in machine learning. So it's kind of a key part to the proof of why expectation maximization works, which is another kind of foundational technique. Okay, so coming back to the entropy connection, so remember that Brice was explaining that the entropy of a probability density, you can think of it as telling you the average number of bits that you would need to optimally encode random values that are sampled from that probability density. And what do we mean by optimal? What we mean is that you're going to base your encoding on your knowledge of the true distribution. So in the horse example that he gave, right, there's one horse that wins most of the time. So you want to use just a single bit code, 0, for that one horse, because that's going to be the most efficient. It's going to crop it most often, so that will reduce the average length. But let's say that you didn't know what the underlying distribution was, and you made a guess at it, Q, and so you're using the wrong distribution. Okay, so you actually think that it's a different horse that's going to win most of the time, so you're going to give that one the shortest code. So in that case, you're going to have still an encoding, but it'll be less efficient. Okay? And so there's a thing called the mutual entropy, which measures the average number of bits needed to encode X that actually comes from P, but you've used an encoding based on Q. That's the mutual entropy. And in fact, the KL divergence is basically just the mutual entropy. Okay, so more formally, the mutual entropy is the entropy of P. So basically the number of bits with using the wrong encoding Q is equal to the number of bits with the optimal encoding plus the KL divergence. So it's basically the extra number of bits that you're going to need because you didn't use the right, you didn't use the optimal encoding. Okay. So information theory is kind of there's a lot of deep connections, and it gives you kind of interesting new ways of understanding, for example, this distance measure. The reason why we call it the KL divergence rather than the KL metric is because by now I think you realize that it's just not a normal metric. This asymmetry that has all these weird properties. So I still don't really understand why it's a divergence. That doesn't sound good. Okay, so the way we're going to use this is we're going to fix P over here. That's going to be our posterior, given the data, and then we're going to vary Q around this family. Okay, so I want you to here's an example. So I've plotted here. This is the probability density P, the shaded blue region, and then I've shown you two different possibilities, two members of the other family. And so I want you to discuss which one of these is going to be closest. Is Q1 closest to P or Q2 closest to P? And answer that separately for the forward. So we call this the forward when the fixed one is on the first position, and the reverse, which is when the fixed probability density is in the second position. Okay, so this is a little tricky to reason about, but once I explain, once kind of show you the answer, I think you'll be able to remember it really easily. And so this is actually an important example because what's going on here? The thing that I've drawn as the true posterior that we'd like to measure. Often when you have very high dimensional data, the true posterior you're interested in is often multimodal, which is just a fancy way of saying it. There's different solutions, right? So there's different parts of the parameter space. They're disconnected from each other, which are all, okay. In this case here, I don't have them as the same heights. So you often are really dealing with something where the posterior after has multiple bumps in it. And so really this is a question that when you move around your family of approximating probability densities, what is your goal here? Are you trying to latch on to the best single mode? Or are you trying to kind of make some summary of all the modes? Right? That's really what these Q1 and Q2 represent here. So it's important to know depending on whether you choose the forward or reverse KL as your measure of distance, what you're going to be accomplishing. Okay, so the answer is that the forward KL is going to choose the Q that covers all of P. Okay, so to explain that, to help us reason this out, so what I've plotted down here are the integrands for the forward KL in green and the backward KL in red. So remember that the distance we're going to come up with is the integral of this thing. So the green has a smaller integral than the red, and I've actually put the numbers right here. So it's about 0.8 for the forward and 4 for the backward. Notice how the integrands do go negative, but in both cases, there's more positive than negative. So that's why the distance ends up being positive. So the way to think about this is when you use the forward KL, effectively what you're doing is you're just taking a sheet and just kind of dropping it over your probability density. Okay? So if you have a whole bunch of modes, it's going to cover them all as best it can. Okay? This green doesn't actually look like a sheet because it's normalized. But if we just think about the shape, what's happening? Well, it's not a sheet. It's maybe something a little bit stiffer. I don't know. And so when you use the forward KL, the closest function is going to be something that covers all of the different solutions in the function that you're after. And that's just because of this property here, because of the asymmetry, you never want to have the thing in the second slot, Q in this example, ever go to 0. Okay? Because the thing in the second slot, if that goes to 0, it blows up to infinity. Okay? That's what we're trying to avoid. Okay, so that's why this red solution is bad, because it goes to 0 here, right? And it's not quite 0 because these are all nice Gaussians. But you see, we're getting we're getting a big contribution out here, where it's close to 0. So that's the forward KL. So it's like kind of dropping a sheet over the target function, and then the reverse KL does the opposite. Okay, so now we've got P in the second slot. So we never want to have any Q where P goes to 0. Okay, so that means that this kind of averaging sheet dropping solution here now has a big blows up because the target function is close to 0 here, the blue P distribution. So in that case here, we get a much better solution if we pick one of the modes. Yeah?
So what if you find the product of the power and the reverse as like a more symmetric measure for this?
Sorry, can you start again?
If you find the product of the power and the reverse, would that be a more symmetric measure?
Oh, interesting. So the product of the forward and the reverse. Well, so that's a good idea, right? We've got this weird thing that we've got this asymmetry, but yeah, of course, we know how to mathematically take two things which are kind of symmetrically related to each other and combine them into something that's overall symmetrized. So product would be one way. Another way would be to take the sum. And I'm actually going to show you that there's a name for that. There's a particular way of symmetrizing it that has nice properties, and it's named after some other guys, Jensen and Shannon, and it is basically a symmetrized version. But it actually uses a sum. It's more like a sum than a product. Yeah, but that's a good idea. Remember that, because when tomorrow, when we talk about VAEs and GANs, okay, we're going to see that VAEs essentially are using the KL divergence. GANs are using the symmetrized Jensen-Shannon divergence. Okay? So this KL that we're talking about now is really fundamental to understanding both VAEs and GANs. Okay, so which one do you want? You know, they both have useful properties. One summarizes all the modes, but kind of averages it all out, and one will pick a mode. Well, in practice, for variational inference, you don't really get to choose, okay, because just the practicalities of being able to do the calculations force a particular choice on us. So to understand that, remember Q is a PDF, and so the KL divergence is just integrating over the PDF. But whenever you've got a PDF, one thing that's usually pretty efficient to do on a computer is to draw samples from that PDF. And if we look at the integral form, I have to go back a little bit. So this integral form, whenever you have an integral and you have you can think of Q here like a weight, and it's actually a really nice, well-defined weight because it's a probability density. So this integral is just taking an expectation value of this piece right here over Q. And you can always numerically approximate an expectation value by just taking the average of this piece here, where your Q is drawn from a Q random number generator. Okay, so if you have something that can make samples of Q, I can just replace this integral by I draw random numbers sampled from Q, and I plug them in to this. Remember, P is fixed. Okay, so that's basically going to be like a Monte Carlo integral approximation to the integral. And all I need to do that is a way of drawing samples from Q. You get to choose Q, so you can choose something, a Q that makes it easy to sample. So with that in mind, we can actually rewrite the KL divergence formally as a difference between two expectations. Okay, so the reason there's two terms here is because we took that log Q over P and we just rewrote it as log Q minus log P. But it's always the same Q prefactor here, right? And so it's an expectation of log Q using samples drawn from Q minus an expectation of log P also using samples drawn from Q. So this form here is the key to doing this practically on a computer, because this lets us numerically estimate using samples from Q. And so this approach here, this kind of using this expectation form instead of the integral form, that's what's known as stochastic variational inference, because the stochasticity is coming from the random numbers that we use to sample. Okay, but this makes it clear why for practical calculations we have to use the reverse KL divergence. Because for the reverse KL divergence, what we need is samples from Q. If we were to do the forward KL divergence, we'd need samples from P. Okay, but the whole problem is that we don't know how to sample from P. Okay, so we don't actually have a choice. We have to use the reverse KL divergence. So that's the one that's going to pick a particular mode from your solution rather than summarizing all the modes with some sort of average. Okay, so just to summarize then, so doing stochastic variational inference means that we have to be able to sample from Q. So every point in this space here, you need to be able to draw random samples from that corresponding probability density, and you have to be able to evaluate both log Q and log P. But once you've done that, stochastic variational inference is trivial. Okay, so here it is in two lines. So Q and P here are just psi-P stats distributions. Psi-P stats has a nice family of pretty much any continuous and discrete distribution you've heard of, and lots you've never heard of. So it's a nice way of kind of prototyping stuff like this. So whatever Q is, it's going to have a random variable sampling method. So I just draw 100,000 values of theta. And then to calculate this numerical estimate of the KL divergence, I just, at all of those Qs, so I calculate the log of the PDF of Q, take the average of that, and subtract the log of PDF of P at each of the random points and take the average of that. Okay, so those two lines is a general completely general numerical estimate of the KL divergence. So here, for example, I use a normal distribution with different sigmas. I check that the KL of Q with itself is 0, and you can also see that it's asymmetric. Q and P and Q give you different numbers. Okay, so there was a lot of equations there, but in the end it just boils down to two simple lines of Python. Yeah.
I don't know what P is, right?
Right. Well, I mean, you know how what you know about P is you know how to evaluate log P. Right. So yeah. So remember. So P is. I think I'm going to actually show that in a minute. So, but P is the posterior. So it's the likelihood times the prior divided by the evidence. Yeah.
Sorry, I'm also confused by this. So I'm not really sure I understand this because you said that we don't know P. So P is actually what we want to approximate with Q, right?
Yes.
Yeah, but here you get to pick P as a Gaussian distribution. I'm not sure.
No, this is just for this example of calculating. So
but in the return you need to know what P is to calculate the.
exactly. Yeah. Okay. Good point. So I haven't explained that yet, but I will. Yes. Because basically everything I've said so far is really there's nothing Bayesian. P is just some arbitrary distribution, and we've got one distribution that we fix, and we've got another family of distributions, and we want to just find the closest one. Okay. So now, let's get more Bayesian. So just what I said. So it's a generic method, but for Bayesian inference, the P that we're going to care about is this thing here, the posterior. And remember we showed that the posterior is just a shorthand for the likelihood times the prior divided by the evidence. I dropped the comma M's on everything just to make the notation a little cleaner, but remember that we still also have hyperparameters in all of this stuff here. Okay, so are we done? No, because the whole problem of practical Bayesian computing is that we can't evaluate this. In particular, it's this piece here that we can't evaluate. Okay, so I still have to show you how we can work around that problem that we don't know how to normalize that posterior. But the other pieces we can calculate, right? That's a likelihood. So, I mean, if you have a model, you know how to forward calculate the likelihood. And then the priors, I mean, you just have to dream those up. What are your priors? You get to pick what your priors are. So we have, the things in the numerator are not a problem. It's the denominator. Okay, so in practice then, variational Bayesian inference has 3 steps. You're going to define the family of probability densities that is going to approximate the true posterior. So you're defining this thing here, and it's going to be a function of the parameters. Any point in this is a function of the parameters that you're interested in, like the age of the universe, but then these kind of technical hyperparameters which move you around the space. I'll do this in a different color. So S are just the degrees of freedom that let you explore that family. So you have to define that family. So it's not quite as turnkey as Markov chain Monte Carlo, because there you just need to code up log of the numerator. So here you actually have to think about what family you want to use. And then we're just going to use optimization to move around the space. So vary these parameters that move you around this space to find the value that is going to minimize the KL divergence. And then you will just so once you've done that, you'll lock in those technical variational parameters, and then this will be your proxy for the posterior. It's not going to be exactly the posterior, but it's going to be the closest you can get with now a function from your family. And then you would use that for doing all of your calculations of expectation values, marginalization, whatever. So in the same way with Markov chain Monte Carlo, you end up just with a big chain, a big basically table of samples, and you use that for doing your calculations. With variational inference, you end up with a function, a probability density, and you use that for your calculations. So you actually end up with an analytic result rather than kind of a numerical table of values. So the main trade-off, though, in doing this is picking the approximate family Q. So if you do more work and in understanding the structure of your posterior, and adding, carefully choosing the degrees of freedom to try and make this family here and as close as possible, or ideally even encompassing the true posterior, then you're going to get better results. But it also is more work to set up. Just to caveat here, so in machine learning, usually the theta, these thetas here are known as the latent variables, and S are called the variational parameters. Okay, so I've told you that the specific probability density we're interested in is this thing here. So now let's actually plug in. So this has three pieces. Let's plug that in, this P of theta, into the definition of the KL divergence. Okay, so we had the log P piece now gets split up. I'm just distributing the log with plus here. And so we end up with three terms like this. So this is just a constant, so the integral over q just gives us 1, so that's just, we get that piece here. The piece that we get in the middle is going to be q log q over big P, so that is just the definition of the KL divergence, but it's not the KL divergence of our family with the posterior, it's our family with the prior. Okay, the prior we know, you chose the prior. And then this last piece here, okay, so the first is the log of the evidence, the thing we don't know how to calculate. The next is the KL divergence of our family with the prior. And the last is the Q-weighted log likelihood of the data. Okay, so you know how to calculate this, and you chose this. Okay, so I want you to just take a few minutes to discuss this question. I want you to describe to me, so what Q would minimize the contributions of each of these terms? We want to minimize this whole thing, but let's just think one term at a time. What Q is going to minimize each of those terms separately? Okay, so just take a few minutes to discuss that. Okay, so let's see where we are. We have 3 terms. We want to minimize their sum, but let's talk about minimizing each of them separately. So how do you minimize this first term, the log of the evidence? You can't do anything about it. It's a constant, right? So this piece here is not going to affect which q is closest to p. Well, that's great, right? Because that's the thing that we can't calculate. So we've managed to isolate the thing that we can't calculate into something that doesn't matter anymore. Okay? So the second piece, the KL divergence of q to the prior. So what is that going to do? How do we minimize that? Make them equal, right? We've got q is a probability density, the prior is a probability density, the smallest they can be is 0. So that is going to drive our function to look like the prior. Okay, so we've really got 2 different functions. Here we have the prior. So that is going to pull q to be close to the prior. And then we've also got the likelihood. So this last term here, what q is going to minimize that? That's not so easy. One kind of way of finessing the answer is to notice that this thing here, minus integral of some probability times the log of another probability, that's the mutual entropy between q and the likelihood. And so the way you minimize that is that you want q to prefer parameters that explain the data, that make the data very likely. Okay, that's the way you minimize maximize the entropy here. And so, but if, roughly speaking, what that's doing is it's pulling you to a solution that explains the data. So here we want q to be like the prior, and here we want q to explain the data. So we have this tension between these 2 terms, and the first term is not doing anything. So here, just kind of wrote down what I said for you to refer to later. But the key point here is that competition between the last 2 terms, that is the essence of learning, okay, of Bayesian learning. Because Bayesian learning is all about setting a competition between your prior knowledge and the information that you're getting from the new data in an optimal way. So if you have crappy data, you're not learning much, and the prior is going to dominate. Okay, so we're going to end up with something that's very close to the prior. If we've got really good informative data, then the prior won't matter, and we're going to end up on this solution. And then, of course, you have a continuum between those, and then you're going to get something that compromises between the prior and explaining the data. Okay, so this is really learning. This is machine learning that's going on when we minimize the KL divergence. Okay, so just to be a little bit clear about how the evidence fits into this, so I can just rearrange the equations I had before to put the evidence or the log of the evidence on the left-hand side. So it looks like this. So that last term is always positive. It's greater than or equal to 0. So it's any KL, it's greater than or equal to 0. Okay, so I mean that's the thing that we're minimizing here. But now I've got it on the right-hand side. Now all I'm going to do is I'm going to say it's greater than or equal to 0. So I can throw that away and put a greater than or equal to there. So now what I've got is I've got a lower bound on the log of the evidence, otherwise known as the evidence lower bound, the elbow. Okay, so the elbow is just this thing right here, and you can do some more algebra to write it out like that. And notice now here we've got it into a form where these are just expectation values over q. There's a q weight there and a q weight there. So it's the expectation of this thing here, the numerator of the posterior, which we can calculate, and the log of our approximating family. So everything here we can calculate. We've just got a difference between two expectation values. Okay, so the reason that we introduce the elbow is because the elbow is basically if you just ignore the piece that you can't calculate, that constant log evidence, then KL is just equal to minus the elbow. And so the crucial insight then is that we actually don't ever need to say anything about the evidence. We can just minimize this negative elbow instead of minimizing the KL divergence. It's totally equivalent because the surface that we're minimizing in is just getting a constant offset from the evidence. And so that's why we're able to use variational inference for doing practical Bayesian computing. So hopefully that answers the questions we had earlier, like, oh, I don't know P, but you don't need to know P. You just need to know the things that go into the elbow, which are the likelihood and the prior. Okay, if you don't know how to calculate the likelihood and the prior, you haven't really defined the problem yet. So. Okay, and then crucially, for practical work, then you can evaluate the elbow you can write it in this expectation form, and then in practice, we're going to take samples of Q, so just make it a noisy numerical approximation to this. So we'll just get samples of Q, so that those same two lines I showed you before, but now instead of an arbitrary P, we're going to plug in the likelihood times the prior.
Sorry, you don't want to minimize elbow. Don't you want to equal the log prior?
No, equal.
But you're trying to minimize the left-hand side of the exponential together, the distance. Aren't you trying to minimize the distance between the KL cubed and 2?
Right, so we want to minimize this, the minus elbow.
Why don't you want to turn that into log prime so that becomes 0?
Well, this is just a constant, so it's not. I mean, 0 is not the minimum value here. It can go negative. No, so that's not right. Yeah, yeah. So you're always going to get. So the distance you're going to get is just that. If your posterior is not inside the point, you're going to get that, the closest point in the approximating family. I guess I don't understand the question. Okay. Okay, so let's just do a quick example. So suppose that we observe some one-dimensional data, so some values of x, and we're going to model it with an exponential. So that tells us what our likelihood is. So the likelihood for a single observation, so it's the probability of a single observation given our parameter theta. So theta here is just the location. I'll show you a graph in a minute. It's the location, the thing where our exponential is centered here. So that's the data and the single parameter. We have a bunch of observations, and we assume they're independent, so we just need to multiply the probabilities, the likelihoods of each of those to get the overall likelihood of our data set. So this is the corresponding posterior. So I just showed you the likelihood. In general, this is not a simple distribution because we have our data. We have random data in here, and so this posterior is going to reflect the random statistical fluctuations in our data. But it turns out that it is roughly Gaussian. So it makes sense to use a family Q that is Gaussian. You definitely don't have to do this. You can use any family you want. To keep it simple, I'm going to fix mu, the mean of my Gaussian, to 0. So I just have one variational parameter, which will be the sigma. Okay, so what that means is that this blob here is now, so in the space of the parameter theta, it's varying my family means that I'm going to be changing the sigma while keeping the mean the same. So it's just a one-dimensional variation. Okay, so it's really the simplest possible problem here. So this is what it looks like. So this problem is simple enough that you can actually calculate exactly what the posterior is. So the thick blue line is the true posterior. Here I'm showing you the dashed lines are just different members in that family here, like I sketched here. So each one of these is a Q of theta for a different value of sigma, which moves us through the approximating family space. Here is the, so what we're going to do is we're going to vary the sigma here to find the best match, where we measure the best match using the KL divergence. Okay, so I plotted here the integrand of the KL divergence for each one of these three ones here. And as you can see, when just by eye, the green and blue ones overlap the best, that's when you get the smallest integrand overall. Okay, so the green is the best match. If we actually, here I've just shown you three different points, which are these 3 points here, but you can calculate the KL, or actually the negative elbow, for all of these points along the line. You get a nice smooth curve. So this is something that's easy to find the minimum just using standard optimization routines like in SciP optimize, or you could also use TensorFlow or PyTorch to calculate the gradients and find the minimum here. And then in the data space, remember we have three different spaces here. We have the space of the data, which is here. This is a histogram of the data that I generated. We have the space of the parameter that we're interested in, okay? And the parameter, you can see the parameter in the data space. This is the likelihood for three different values of the parameter. So the parameter that we're trying to infer here is we have this exponential, e to the minus absolute value of x, and we're just sliding it left and right. That's the parameter we're trying to vary. That's our second space. And then our third space is the variational parameter. And that's what's shown up here. Here we're varying the variational parameter, and as we do that, we calculate a different distance between the true posterior in blue and the member of the variational family. Okay, so there's a lot to keep track of. We have data, parameters, and variational. And here I've chosen an example where each one of those is one-dimensional, but in general, that won't be true. Okay, so the kind of the cognitive load here is definitely higher than Markov chain Monte Carlo, but the actual calculations are often a lot more efficient. Okay, so how do you let's be a bit more practical for more realistic problems. So a really nice thing about doing Markov chain Monte Carlo is that, especially with Metropolis Hastings, it's a total black box. You just need to code up the likelihood and the prior. So just write functions that can evaluate those for arbitrary parameter values, and you just plug it into a black box, and lo and behold, you get Markov chains coming out. So variational inference is a bit more brain work involved. You have to set up the problem. In particular, you need to think carefully about what approximating family you're going to use. If you just always pick a Gaussian, you're not going to get very good results. So. But once you've done that, it's often computationally a lot more efficient because you're replacing sampling in the Markov chain with optimization, which is just inherently a more efficient process. And of course, to do any VI inference, you have to select that approximating family, and that requires you to know something about the problem, more than you need to know just to jump in to doing a Markov chain. And you need to use your judgment on how to trade off the calculational convenience. How easy is it to sample from that distribution? If you make your distribution really complicated, it's going to be hard to sample from. But also you need it to be complicated enough that you expect to get close in the KL sense to the true posterior. Okay, so once you've actually selected your family, then what you need to be able to do is you need to evaluate the minus elbow, which is just our proxy for the KL, because they just differ by that constant log evidence. And you need to then be able to optimize by finding the value that's going to minimize that divergence. So there's standard numerical optimization methods to handle the second step. And the first step, instead of doing the analytic integral that defines the elbow, what we do is we use stochastic variational inference and just generate samples of Q, and then use those to evaluate this, take the mean, evaluate this, take the mean, and get the difference. So it's just the 2 lines of Python that I showed you before. And the things that you need to be able to calculate, the likelihood, the prior, and evaluate the density for the current approximating function. Okay, so just to finish up on this topic, I just want to kind of come back to the Markov chain Monte Carlo and show you that it actually is, in some sense, also minimizing a KL divergence. Okay, so remember, for variational inference, we use the reverse KL, and we don't really have a choice about that because what we're doing is we're going to computationally, we're drawing samples from Q, and then that's how we're going to evaluate the distance between Q and the posterior. But if we think about what's going on in Markov chain Monte Carlo, so that actually gives us samples from the true posterior. Okay, so once you've run a Markov chain, you actually have samples of P. So that means that you can actually calculate not the reverse KL, but the forward KL. Okay. And so to contrast these, what variational inference is doing is it's finding the Q that is closest to P according to the reverse KL. But then using a Markov chain, you can actually find, if you define an approximating family and plug it in here using the samples from your chain, Markov chain Monte Carlo lets you find the member of the approximating family that's closest to P according to the forward KL. Okay, so you actually, you can choose whether you want to do the forward or the backward. And remember that kind of heuristically, they're doing quite different things. The reverse KL is basically finding the best mode in your multimodal posterior, whereas the forward KL is really kind of summarizing all of the modes together. It's like dropping the sheet over the probability densities. Okay, so I'm going to change gears now and just start on the second topic, second lecture topic. Okay, so I think as we go through this, it'll be clear how this topic is intimately related to what we were just talking about. But the theme here is unsupervised learning. And so in particular, we're going to talk about doing unsupervised learning from astronomical data. I'm going to focus really on astronomical data and using neural networks in particular. And so the main applications of unsupervised learning that I have in mind are three. So first is dimensionality reduction. So you have some data, and you're asking the question, how can I represent the data that I have more efficiently, and then perhaps get more insights into its data, into its structure. So in astronomy, our data is often in the form of images or spectra, but it's pretty sparse in terms of the information that's there. And so it can be very useful to come up with, instead of having megapixel images, to come up with some low-dimensional representation that captures the essential features. So that's what I mean by dimensionality reduction. So that's an application of unsupervised learning. And then the other two are kind of related to each other, generative modeling and probabilistic modeling, but they're answering slightly different questions. So in a generative model, what we're doing is we're asking, how can I interpolate or even extrapolate from a small, sparse data set to generate new data that's sampled from the same unknown distribution? So what I mean by this is that you've observed some data. Say you've collected 100 spectra, and then in some space, they're pretty sparse. And what we'd like to be able to do is we'd like to be able to ingest those 100 spectra and now generate new spectra, random spectra, that somehow fill in the gaps here and even go outside of it, which would be extrapolation. So let's say I've observed 100 of these, but now I want to generate 1,000 of them, which are drawn ideally from the same underlying distribution. So when you do that, you've created a generative model. And then the other is a probabilistic model. And so in a probabilistic model, you have the same 100 of spectra. And now I'm going to give you a new spectra, which I've observed. and I want you to tell me what's the probability that that new spectrum came from the same underlying distribution as my 100 spectra that I already have. Okay, if it's out here, the probability is low. If it's in here, the probability is high. But actually quantifying that. Okay, that would be a probabilistic model. Okay, and then some of the jargon that we're gonna cover in this lecture: PCA, VAEs, GANs. We'll be learning, talking about all that stuff. Okay, so unsupervised learning. So the way I think about unsupervised learning is I first kind of think, what is it? What is data really? And so to me, data is just it's just a two-dimensional table. It's a spreadsheet. Often our data, we think of it as being much richer than that, but machine learning algorithms, always kind of flatten your data down to this pretty boring and uniform structure. So data, it has columns and it has rows. So the columns represent the features that we measure, and the rows are the different observations or samples of our data set. So, okay, so you might say, well, an image is clearly not, it's not just a one-dimensional thing, but you can always take the image data and just flatten it out. Or if you've got a data cube, you can do even more flattening. And that's generally how machine learning algorithms think about your data. Okay, they don't care about the kind of two-dimensional or three-dimensional relationships, because they're generally just going to flatten things out. And so the essence of unsupervised learning is to treat this data in a holistic way. Okay, so that means that you don't view any of these columns, these features, as playing any special role. So they're all on an equal footing. And then given that perspective, then you just look for patterns in the data. Okay, and so to contrast that with supervised learning, in supervised learning, what we do is we're going to kind of designate some special columns, one or more, okay, in the data. And we'll think of those as labels. So we'll think of this as somehow labeling each observation. And then we're going to try and learn a map. If we call the rest of this stuff X, we're going to try and learn a map from X to Y. So supervised learning is learning a map from X to Y. Unsupervised learning is just treating all of the features on a equal footing. And so in the language of probability, unsupervised learning is just learning a joint probability distribution over all the features. And supervised is learning a conditional probability distribution. What's the probability of a label given the other features in the data? Okay, so just a comment about data sets. So the progress in machine learning, outside of astronomy, has really benefited enormously from having these really well thought out and curated public data sets that have been studied to death now. I mean, anyone who writes a paper, it's mandatory that you have some tests on one or more of these data sets. So, for example, in images, kind of the main data sets are a thing called MNIST, which I'm sure you've heard of. So it's just these handwritten digits. They're just tiny images. They're 23 by 23 pixels. You can see the pixels there. They're just grayscale, so no color to worry about. And there's 10 categories, the 10 digits 0 through 9. So how many people have ever done anything with MNIST? Okay, so it's kind of like, it's the hello world usually of most machine learning algorithms. Another one is CFAR 10, and there's also a CFAR 100. So this is pretty similar, except instead of just there's only 10 categories again. So like the handwritten digits, they're a little bit bigger, 32 by 32, but they're actually natural images. Okay, so can you tell what that is? It's actually really much harder to tell when you're up close, but from the back it's pretty easy. So that's some kind of dog. And that's one of the 10 categories, dogs. So these are pretty low resolution, but it makes the problem it means you can actually get results pretty quickly. And but there's only 10 different categories. And then we have ImageNet, which is much more realistic. So these are real photos. They have different aspect ratios, different sizes. Both of these are they're color images, so they have RGB. So kind of the astronomy analog would be different filters. If you have the 5 Stone filters, but they're varying sizes. The average is about 470 times 400, and these are labeled with 1,000 categories. And I don't know who picked these categories, but they're not it's not a very general purpose set of categories because they include 90 different breeds of dogs here. So people who do a lot of research with ImageNet, they get really good at recognizing different types of dogs. So. But most people can't recognize, can't distinguish 90 different breeds of dogs. So it's trying to do a problem that's well beyond what most humans can do. So, but it's a comment I want to make though is that if we look at the ML community, so this has really enabled them to make a lot of progress, and we need similar resources for astronomy, machine learning research. So if you're still looking for a project, something to do, or just maybe later on. For your thesis, you need some sort of data set. Think about not just doing a data set for yourself, but how you could really be a superstar in the field and make your own equivalent of MNIST for galaxies or quasar spectra or whatever. So we need that. Okay, so I want you to just take a moment and discuss. I want jot down on a piece of paper some ways in which astronomical images, here's a not very typical one from Wikipedia, are different from typical natural images, so photos like this. And in particular, think about what are the ways they're different that matter for machine learning? Okay, so just jot down a couple of ideas about what are some important differences, and I'll ask you to call out different ideas, and we'll make a list on the board. Okay, so give me some ideas. How is a dog different from a galaxy?
Dynamic range.
Dynamic range. Good. Which has the larger dynamic range? Yeah. So if we okay, specifically if we just look at the range of values in a single pixel, right? All of these images in these standard data sets, they're just 8 bits per channel, right? So in terms of intensity, you only need 256 levels to represent, a whole universe of different types of objects. But in astronomy, right, when we work with fluxes, kind of photon counting units, you need many orders of magnitude to capture the interesting range. So another.
Sort of going along with the same idea, but focus is so with a camera, when you're looking at things that are nearby, some things are out of focus, some things are in focus. All of our sources are at infinity, so we have everything's in focus.
Yeah, that's interesting.
You have the flaring of the atmosphere, you have the telescope. You do have a lot of.
But everything is affected the same way by that.
Depends on the telescope.
From data set to data set. Depends on the.
So this
Well,
is
yeah,
half of the
specifically across the image, yeah.
This is not a typical image.
Well, it depends what your research is, but no, that's a good point. Okay, so there's basically you have finite distances, so you get depth of field effects. A lot of photos, artsy photos, people try and have the subject in focus and the background blurred, and that just doesn't happen in astronomy. So you're right that you have a PSF, the atmosphere, or even the instruments for space instruments, is going to blur it, but it's going to uniformly blur everything. Everything is at the same. In a given exposure, you'll have a uniform blurring. So it's a different problem. Okay, but that's. So versus the atmosphere and the PSF. One actually subtle way in which the PSF is really is a nasty is for ground observations. So think about what happens when you take this photo of the dog. Where do the red, green, and blue channels come from? Okay, you press the shutter once, and basically the sensor, the CCD or the CMOS sensor in your camera, it's really a grayscale sensor, but then there's a little grid of red, green, and blue. It's called a Bayer array of little filters over every pixel. So you're simultaneously taking the red, green, and blue images, but that's not how we do it in astronomy, right? When in a like Sloan or DES, so they'll take a picture with one filter. Let's focus on DES, right? Let's say they take the G-band filter image, and when's the R-band filter? Is it taken at the same time? No, it might be a week or a year later. Okay, and so is the atmosphere going to be the same? No. So you can have very different observing conditions for the different filters. So although you can stack them together to make color images, if you do that in a naive way, you're introducing artifacts, because you might have one day when the seeing was really good, and the other day it was really bad. And the same for the sky background; it can change a lot. So in astronomical images, we're taking each of our bands under different observing conditions. So something else. Something else is different? Brent? Signal to noise ratio. Yeah. So is the signal to noise ratio in astronomical images generally higher or lower than in photos? A lot lower. So this is not a representative example. This is some long Hubble exposure. Yeah, so I mean, certainly for my work, where I deal a lot with postage stamps of galaxies, but they don't look anything like that. Okay, they just look kind of like a smudge, if you're lucky. And in LSST, each exposure we're going to collect our weak lensing sample. We in each exposure of a galaxy, we're collecting on the order of tens of photons. Okay, so that does not give you this. So signal to noise is really low. Yeah.
Yeah, what we know about the two images is really different. So we know that this dog, this is a sufficiently described dog, and this being a spectacular
Yeah, very good point. So the way I'm going to summarize that is priors. So in particular, it's actually not crazy to write down good priors for astronomical images, right? So you've probably heard of Search profiles and Moffett models for PSFs and stuff. So those are basically our priors for what astronomical images look like. When we look at a galaxy, especially at low signal to noise, you don't see any of this substructure in the galaxy. It's just a Gaussian blob that's mostly telling you about the, if it's a small galaxy, mostly telling you about the blurring of the atmosphere and a little bit about the galaxy structure itself. Okay, so we have simple models at Search that can describe that. And those basically translate into priors. We can write down good priors. Can you write down a good prior for anything you can point a camera at? No, so that's a really hard problem in vision, is that there's no sensible priors. We don't have models for what the world, the natural world looks around us. And so that's why a lot of the machine learning, a lot of this, the cool papers that we read, people doing stuff with images, a lot of it's not really so applicable because it's not taking advantage of the fact that we have strong priors in astronomy because you just don't have that in natural images. You had a question or comment in the back? Or further back? Sorry? Right. So we have we have symmetries in we have a pretty high degree of symmetry in our images. That is not true in natural images. And that actually comes in because one of the techniques that we use in order to, if you have a small sample, there's a standard technique that lets you kind of for free reduce the tendency to overfit, and that's something called data augmentation, where you would take each example like this and you would replicate it where you make some changes to it to pick images which are in some sense equally likely. And so I'm going to talk about that more soon, so I'll come back to that point, but that's a good point. Yeah.
This is maybe more relevant for the supervised stuff, just as kind of a counterpoint to the priors. We often, in terrestrial images, definitively know what the thing is just by looking at it. But for astronomical data and images, we often don't have a higher expert authority to appeal to know, is this low signal noise galaxy really a spiral or a blob or whatever? So kind of, it's approached through the image in the sense that there's not an obvious right answer for us.
Okay, that's interesting. Yeah. I would say countering that is the fact that for a lot of astronomical images, we can actually make simulations. Right? It's really hard. You can't really simulate natural images like that. But we have programs like GalSim that can you can just put in. So if you have some model, like you may not know what it is, but if you have models for the different hypotheses, you can actually generate a large sample of for hypothesis 1. This is a sample of images, hypothesis 2, and then so that actually gives you a pretty powerful, yeah. But you're right. I mean, you don't often have really the same kind of ground truth, right? You can always just get a little closer to that dog or take its DNA, and you know exactly what it is, right? You don't. Yeah.
And not an expert, but
in dogs, or
always been wondering that because the feature is so well defined, and in the past people have done various transformation to decompose images. So it's unclear that the images, the raw space, is the best place to do the feature extraction because you can do some simple transformation, which makes the training much simpler.
yeah. So I think. So you're right that the raw, just the flattened pixel values in here is almost never in any like an efficient or optimal representation of data. But it's what we start with, and so you.
You think about like that is a spiral galaxy, so
Mm-hmm.
you can use a different transformation to figure out the spiral arm and stuff. And this is why in the past even simple analytic decomposition can do a pretty good job. So you also wonder like in the era of ML, how much we still use some of those
Yeah. Yeah, that's a good point. I mean, even for something complex, I mean, this is relatively complex by astronomical standards, but you can still come up with mathematical models that do a reasonable job, and it's pretty hopeless to come up with a mathematical model for a pooch. So. Okay, so here's the list of things that I came up with. So there's a few we didn't mention. So one is that, kind of coming back to the priors, the objects that we're dealing with are, they're inherently pretty small. Okay, not small if you're standing next to them, but small from our, viewed from Earth, and they have relatively simple shapes. Okay, so just the kind of the morphology, especially when you blur things by the atmosphere, is generally pretty small. Another issue, especially it's important for the work that I do on when galaxies are overlapping or blended with each other, is that the objects that we deal with are generally transparent, right? So if there was another galaxy right here, what you would be seeing, the foreground galaxy wouldn't just cover up the background galaxy, right? When I'm standing in front of the screen, you can't see the screen behind me. But if I was a galaxy, you'd be seeing a mixture. Okay, so that's something to deal with. And also you don't have like hard edges. So there's a whole nice work on object detection. But basically, so you take a photograph and then you draw rectangles around, automatically find rectangles around all the objects and identify what they are. But that often doesn't really even make sense for an astronomical image, because you might have two galaxies, and you're seeing them through each other. So the idea of a bounding box is a little less well defined there. Low signal to noise, we mentioned that. The different bands, we mentioned that. Another issue is that the background, after you do your sky subtraction, actually has a well-defined value, right? So these values are 0. Okay, there's some noise, but essentially they're 0. And that's actually a really strong prior that is generally not taken advantage of if you just use kind of algorithms designed for these types of images. Because the background here is just whatever is behind the dog, and that can have any pixel values, right? It's just there could be trees here, it could be buildings, it could be anything. In this case here, it's out of focus, making it pretty easy. But the background in a natural image is some very complex thing that you can't really characterize in any precise way. But for astronomical images, the background is something you can actually characterize in a very simple way. It's basically 0 plus it's random noise with a mean of 0 and a variance that we know. Okay, and then another important difference if we're going to use standard vision machine learning methods is that generally we don't want to, let's say we're doing classification and we're trying to say, is this a star or a galaxy? Generally it's not sufficient just to give an answer, right? It's, for most applications, just saying that's a dog is good enough and you're done. But here, if you say it's a galaxy, I want to know more. I want to know how confident are you that it's a galaxy. I want to have some sort of measure of the uncertainty of that classification. So label uncertainties are really desirable in downstream analysis. And if you just go with a kind of out-of-the-box, off-the-shelf machine learning algorithm, it's generally not going to provide that. And then we talked about the simulations. So coming back to the idea of augmentation, so we often augment a sample. So there's the original on the left-hand side, and then these are some of the standard augmentations that are built into the FastAI library. So flipping it left to right, cropping it, so changing the aspect ratio and resizing a little bit, doing a warp. You see this is kind of a warp, so we've kind of shrunken the top and expanded the bottom. Here we're rotating it a little bit. I think the dog looks cuter now. Can you zoom out? It does, right? If you zoom out a little bit, so here, in this case here, we created some empty space and we just filled it in with black pixels. Here, by zooming out, we also created some empty space, but instead what's done here, you see we're actually reflecting the dog above and doing the same thing here. It looks kind of weird there, but it actually works, I would say, everywhere else pretty well. So it's just using a heuristic to fill in, to do something better than just putting in black pixels. We can adjust the brightness, we can adjust the contrast. So I don't want to, I don't think we have time to discuss this right now, but what I was going to ask you is, like, think about which of these makes sense for astronomical images. And here, just to show you, I've applied the same transformation to the astronomical images. So, what we're asking then is, if this is a real galaxy, are these all plausible samples from the same underlying distribution of galaxies? Is there anyone here that which sticks out as not being plausible? Which one? Yeah, what's wrong with this one? Yeah, so you've changed the sky level. If this is an image from space, then remember the background should be pegged at 0. So by doing this, we've now made the background some non-zero value. So it's like we've added some diffuse intergalactic medium or something. So we don't want to add new physics to our images with these augmentations. Zoom is certainly okay. Rotate is okay. We mentioned that galaxies have a high degree of symmetry. Yeah. Yeah, so that's a good point, is that the way we use, often our individual samples in our data set when we're dealing with images are these postage stamps. And by construction, every postage stamp, we've detected an object from a catalog, and we've made a postage stamp that contains that object, yeah. And so that's often kind of just baked into what we mean by our data. But when you do things like that, now it's moving off to the side. So that's fine for natural images, because it's just saying you're a bad photographer and you cut people's foot off or their head off. But that's normally not how we. So if our actual catalog postage stamps were all centered, then this wouldn't be representative of that distribution. For the work that I do, where the shapes of the galaxies are important, I'm trying to detect coherent distortions to the shape due to intervening dark matter, so weak lensing. So this would be a bad thing to do because this is distorting the shape. Okay, it's fine to do zoom and rotate. That doesn't change the shape. But this thing here would introduce new physics, which I don't want to do. Okay, so you have to be a little careful when you just use these standard image augmentation techniques and think about whether they still apply, and are you introducing new physics that you didn't mean to? Okay, so I think I'm gonna stop there, and then so we'll pick this up tomorrow. It'll be the second lecture tomorrow, and what we're going to focus on is on VAEs. And the V in VAE is the same as V in VI. It's variational. Okay, so VAEs are really doing a variational inference. So I'll show you exactly what I mean by that, and we'll see that this KL divergence is really key to understanding what's going on in a VAE. And then we'll also look at the other main kind of generative modeling approach, which is a GAN, or a generative adversarial network. And I'll show you at the end how, although those are really, they have very kind of different historical developments, they are actually connected in some interesting ways. In particular, we talked about a symmetrized KL divergence, and again, actually minimizes a symmetrized KL divergence. So, okay, so that's all for today.